throughout the lifetime of a process, the process changes its state continuously. So, for example, to start a process, to create a process, first you should allocate memory for that process. So you should go to your memory manager in the operating system, find some free space. If not, if available, there's no available space for that, you have to open up some space. We'll discuss how you open up some space, but you have to write something from the memory, for example, to the swap, to open space, and say, okay, I'm going to use it for this new process. So this takes time. Then, even if you have the memory, you should also read the instructions from the executable file, from the program, and copy them into the text section of the process in memory. Now that also takes time. You should initialize the data section. You should create the global variables there and initialize them. And also you should create an entry for main. And if it takes arguments from the command line, you should set the argc and argv arguments of the main function. Set the program counter to the address of the first instruction, and only then the process can run. Okay. Now, during all this time, the process is being created. We cannot say it is created, because that creation itself is taking time. Okay? During all that time, we cannot say the process is ready to run, because it's not properly created yet. Therefore, it is in a state we call the new state. So the moment you start creating the process, you set its state to new, and until everything is ready and the program counter is set to the address of the first instruction in main, during that time it's in the new state. Now, when all this has been done, we do not go into actually the running state. After the new state, we should be in what we call the ready state. So the ready state is a state when the process can now be scheduled. Pay attention, I didn't say is scheduled. It can be scheduled. Now, why not schedule it? Because currently the operating system was planning to run some other process maybe. Not necessarily this new process. This new process has to get in the line to wait for its turn. Therefore, we say the process is ready to be scheduled, but whether it is scheduled or not depends on the scheduler. So there is a second state called the ready state. Now, at some point, the scheduler will say, okay, now go ahead. Now you can use the CPU. So now this state is different than definitely the new state, and also from the ready state, because in the ready state it was ready to be scheduled. Now it is scheduled. Therefore, now the process is in the running state. So a process that is in running state is a process actually that is in the CPU. In reverse, that is allowed to use the CPU. It can execute its instructions in the CPU. While executing its instructions, at some point, the process might, for example, decide to do some I/O operation. Read from the disk, write on the screen, or read from the keyboard, or send some information over the network, send something to the printer, any one of these, or any other thing. Now, all these I/O operations, as we have discussed several times earlier, are quite slow operations. Therefore, the CPU does not want to sit idle while those slow I/O operations are being done. Now assume that you're trying to read from something from the user and the user has gone for lunch. We don't want to waste the valuable CPU time for this guy to return from lunch. Even if the user is just in front of the computer and is very carefully following what's going on, the time it takes for you to react to whatever appears on the screen is too long compared to the speed at which the CPU is running. Therefore, the moment the process wants to do some I/O, its state will be changed from the running state into what's called the waiting state, waiting for something to happen, some I/O to be completed. Or, as we will discuss later, for example, for some signal to arrive. I'm waiting for that signal to come. And you don't keep the CPU busy while waiting for that. So the last state is what we call the terminated state. That is when the program comes to the end of the main function, and there, for example, typically you say return 0, for example. Or you not come to the end of the main function, but, for example, you detected a problem and you called exit, say, -1 in some function, not necessarily in the main function. Wherever you call exit, the program immediately terminates. Or none of these, you tried to do something, but your program crashed. For example, you had a faulty pointer and you tried to access some illegal address, either some address out of your memory space, like you try to access the operating system address space or another process's address space. Or, for example, you try to write something in a read-only area, like, for example, the text section, which is read-only. You cannot change the instructions. Okay, so these are all illegal operations. So the operating system kills your program, terminates your program, because it has done something illegal. Now, when we say a process is terminated, the memory assigned to the process is released, but still some more information still remains in the system for the parent process. Remember, when the parent process forks for a child process, and if the child process has somehow terminated, gracefully or not, the parent process has to know about that. That's why the parent process, for the parent process to learn about the reason of exit, you should keep that information until the parent reads. That's why when a process terminates, not everything is immediately released. Therefore, the process, although it has been terminated, it's not completely gone. So we say the process is, in quotes, in a zombie state. Therefore, there has to be a state corresponding to that, and that's the terminated state. CPU is never allocated to a terminated process, but still, the process is not completely gone yet. So we can explain this state transition of the process state, as you can see in this figure. So the program typically, every program starts in new. Remember, when you're in the new state, the process cannot be scheduled yet because the process is still being created. It's not completely created. So a process in the new state is not properly created yet. It's in the process of being created. Once it has been created, it will be admitted into the system Now it's a completely created process. So the state of the process changes from the new state to the ready state. Again, let me remind once again, when a process is created, it doesn't directly go into the CPU. It has to wait for its turn. Okay, that's why it doesn't go into the running state, but it goes into the ready state. So there are, for example, if you're talking about a system with a single CPU, with a single core, okay, so it's the simplest case. If there are n processes in the system, there can be at most one process that's in the running state. So all other processes should be in these other states. Okay? So a process that is waiting for its turn is in the ready state. Waiting for what? For the scheduler to say, go ahead, use the CPU. Okay? That's called, we say the scheduler dispatches this process to the CPU. Okay? So through the dispatch function of the scheduler, the process switches from ready to running. And while in the running state, if the process completes its allocated time slot, especially when we're talking about the interactive systems, where like your Linux, Windows, Mac OS systems, you will get the CPU for a limited time because we need interaction. So in time sharing systems, we're sharing the time, and we're sharing the time like we're given each a small portion of the time. That's how we share the time. Okay, so you're given the CPU, say for 10 milliseconds. In 10 milliseconds, you run as many instructions as you can. But if when the 10 milliseconds timer expires, the your process will be interrupted with an interrupt, with a timer interrupt, which will cause your process from running state to go back to the ready state. Why? Because actually the process might have continued to run. Okay? There's no problem with the process. The problem is that it doesn't have any time left. That's why we put it back into the ready queue so that later in near future, it again has the option to be scheduled into the CPU once again. Or another thing that could happen for a process that is running is before the timer expires, before its time slot ends, it tries to do some I/O. Therefore, from the running state immediately, although it has some, it still has the right to continue. Sorry, it will be switched to the waiting state. So if you're giving 10 milliseconds and say at the 4th millisecond, you try to do an I/O operation, sorry, but you cannot use the remaining 6 milliseconds. So immediately that process is taken from the CPU. We cannot put it back into the ready queue because to the ready state because we don't know if its I/O operation will be completed by the time we give it the chance to go to the CPU once again. So we should not consider that process for scheduling. That's why we put it in another queue, in what we call a waiting queue, until that I/O operation is completed. And when that I/O operation is completed, with the I/O, or if you're waiting for an event, so in only when that completes, it can be taken again, not back to the CPU, but to the ready queue. Like in the previous example, we said you had 10 milliseconds, you use 4 milliseconds, then try to do I/O. So 6 milliseconds have been taken from you. When the I/O completes, you cannot say, oh, I already had 6 milliseconds, so I want to go into the CPU immediately because I'm going to use those that remaining time. You're not allowed to do that. Sorry, but that 6 milliseconds is gone. So you go back to the ready queue and wait for your turn to be scheduled into the running state, again by this scheduler dispatcher. Okay, so this is how things are running. And at some point, the process will complete gracefully by coming to the end of main function, or due to, for example, an error, and it will exit. Now note that only a running process can exit. A process in the ready queue cannot exit, because if it had already come to the end of the main function, that would have happened while it was in running state. You cannot, there is no progress while you are waiting in the ready queue or the waiting queue. Therefore, exit is possible only from the running state. That's why we have this process state diagram. Now, we discussed about the memory space. Remember, we said there are 4 sections. Let's repeat: text section, data section, and the third and the fourth were together allocated for the heap and the stack. Now, these 4 parts we have in a process. But we also said there are also those registers. Okay, where are the registers? The registers are in the CPU. We have the program counter and the other general purpose registers, which contain the immediate values of your variables, for example, that will go immediately into the ALU for calculation. Now, note that those registers are in the CPU, but when you're taken from the CPU and put back into the ready state, you don't have the CPU anymore. So what happened to the values in the CPU? We cannot put them back in the variables at the moment, because, you know, while calculating those statements, there could be some temporary variables that are used, which are not in your program, but these are typically managed at lower levels. So there should be some space that could be used for such purposes. So we talk about what's called a process control block, which contains some information about the process, but it's not the data section or the text section, whatever. That's some other space, yet another space. So this is actually a small data structure, which contains, first of all, your state. In which state is this process? Is it in the new state, ready state, running state, waiting state, terminated state? Which state? Okay, so in a variable, you should be keeping these values. Where do you keep them? So that's in this field. The process ID, the process number. The value of the program counter. Remember, there's the program counter register in the CPU, but when this process is taken out of the CPU and to be placed, say, in the ready queue, you should remember the value of the program counter, because you should continue from that next instruction. Remember, the program counter has the address of the next instruction. So when you take a process out of the CPU, you should store that value so that later you can restore it when you take it back to the CPU. The values of all the registers at that very moment when you decided to take that process out of the CPU, because again, to continue from where you were left, you will need those register values. Also, any other memory limits, how much, so from where to where in memory, for example, you can use them, such memory limits, and also list of open files. You have opened some files, so you have the file handles, file descriptors, so you should be keeping them also. You could have put some locks to some files, as we will discuss later, that kind of information. So in addition to them, like information related to memory management, so memory limits is part of that. Accounting information, if you have enabled accounting, as we discussed in the previous chapter, in some systems, for example, we would like to put a limit on how much each process is allowed to use the CPU, for example. So how much CPU has been used, how much clock time has elapsed since the process has started, how much memory you have used up to now, how much data transmission you have done, that kind of information. And I/O operations, I/O steps, like the I/O devices that are allocated to this process, the files that are currently open by this process, which file is opened as read-only, which file is opened as read-write. In each file, at which position you're currently, so that we know where to read the next byte from. All that kind of information is stored in what we call the process control block. Now, this information, what you see in here, is for a single process. For each process, we have to store this information. Okay? So it's repeated for each process. So as a process is executing, now read this figure from top to bottom. So the time flows this way. Okay? This is for process P0 and this is for process P1. Of course, there are many processes in the system, but we're talking about a very simple scenario where we have only two processes. But of course, there's also the operating system in addition to P0 and P1. So initially, P0 is executing, and at this point, there is to be a context switch. That means at this very point, the CPU, the operating system says, okay, enough with P0, I'm going to switch to P1. Okay. Now, this is not done momentarily. You have to save the state of process P0 into the process control block for that process P0. So we write into PCB0 the information related to process 0. So that save operation takes some time. Remember, you have to write the state. The process number has not changed. You have to update the program counter. You have to update all the registers. The others typically will not have changed much. You have to store this information. So you should save the state for process 0 and you should reload the PCB value for process P1. This was saved in a similar way earlier. Now we have to restore it. In the, for example, you have to put all register values, read them from the PCB and put them into real registers. And the last thing, the very last thing you would do would be restoring the program counter. Because the moment you restore the program counter, the CPU hardware, the control unit, will read the contents of the program counter and immediately jump to that instruction at that address. And when that happens, you will have jumped into process P1. So from where you were left, you will start executing process P1. And its time expires. Again, save the state into PCB1. And we have no other process in our system. So go back to process P0 by reloading or restoring the value. And from that point on, it runs. Now, there's one thing you should note, and that is, excuse me, from this point to this point, during these areas I'm crossing out, there is something going on. There's the operating system at this moment is doing these save and restore operations. Now, these are not useful operations. Of course, they are required for the proper execution of the processes, but you're not executing your process instructions. This is operating system overhead. So we would like to keep this overhead as minimum as possible. So of course this figure is not to scale, but there is that overhead and we would like to keep that overhead at minimum. Now, up to now, we talked about processes that are running in single thread. That means there is no parallelism. That means your program starts, it executes one instruction after the other. Okay? So we say we're talking about a single thread of instructions. It's like this instruction, after this one, after that this one, after that this one. So we're talking about a single thread. Now, what if at some point I have an option like, while this is happening, also start doing something else. And when that is done, you could merge it here, for example. Examples, like assume that you enter some information and you start a database retrieval from that. That means go to a database, ask for some information. Now that database is a huge one. So you start reading that huge database, and for every record, you're checking if that record fulfills your search criteria. If yes, add it here. If not, look at the next one, look at the next one, look at the next one. Now, if you have thousands of such records, it takes time to go over all of these records one by one. Now, assume that you're also trying to populate, that means fill a list here. Now, one thing you could do is the window that appears here gets frozen. Okay, you cannot do anything there. You have to go through the whole database, which may take tens of seconds. Only after going through the whole database, it returns all of the values. Okay, and then suddenly you fill that list there. So from the user's point of view, this is not an interactive system. I clicked a button and my screen was frozen for tens of seconds. At the end, yes, I got all the information, fine. But for tens of seconds, I was just sitting here until something happened on the screen. Or an alternative design could be that, for example, it starts reading from the database. The moment it finds something, it transfers it to this list. So it's displayed here. Meanwhile, the database operations continue on this other side. So this here we have our main thread, and here, for example, we have our database thread. So this is a very simple example of where you would like to have a multi-threaded application. So now this is one thread running, this is the second thread running. Actually, it overlaps with the execution here. What does it do for us? Now, it first brings us some interactivity in this example, but the more important thing is this is parallelism. Two things are running at the same time. Okay, so this will also help us speed up things, especially if your system is either a multi-processor system. That means you have multiple processors so that one runs the main thread and the other one runs the database thread, or very similar to multiple CPU systems, we have multiple core systems. It's just core is just like a small CPU with limited execution power, but it is in the same chip. Therefore, it runs with less energy and in terms of communications, it's much faster. You can do a lot of sharing between the cores, blah, blah, blah. That's beyond the scope of this course. But using multiple cores is more effective. So if you have multiple cores, for example, one core could be running the main thread, and the other core, for example, could be running the database thread. You can easily find such examples. So we have now multiple locations that can execute at once over separate threads that are running over separate, for example, CPU cores. So you should have multiple program counters now, because the program counter, the PC for the main, would be different from the PC for the database. So there are some variations. Anyways, those are discussed in the next chapter, in chapter 4. Finally, you need some data structure that can store this kind of information. Now, this is just an example implementation for that data structure. Of course, you can find other ways of storing this information, but you need to keep the process ID. You need to keep the state. You need to keep the time slice, the length of the time slice reserved if you're talking about a time sharing system. I need to know who my parent is. So I need a pointer to another PCB, to the PCB of, now this is my PCB, process control block. I need a pointer to the process control block of my parent. Therefore, it's a pointer to the same type of structure. If I have children, then I need, again, now pointer to my children, but I could have more than one children. Now you can have a single parent. Now, these are not human beings. When we talk about processes, a process can have a single parent but multiple children. Therefore, rather than a pointer, we need an array of these children or a list of them. It depends on how you want to store it. Similarly, for the files, I need an array of files or a list of files, again, depending on what type of a structure you want there. And also some information about the memory. What parts of memory are allocated to this process. So you need a structure similar to this one. This is an example structure.